Okay, so 15.7 is on cylindrical coordinates. And I guess I would argue you already know how to do these. Okay, so let's just do a pretty quick little diagram here. Oh, Chris is asking if you could leave the end or unsimplify it. I thought it was pretty simplified, but you know, you're asking me if you should evaluate 3 to the 7th, and you know, I can't imagine taking a point off for not evaluating 3 to the 7th. Normally, I want you to simplify your stuff. Anyway, let's go on. So you've got R, you've got Z, and then let's go ahead and put theta. Theta, as always, is measured up from the x-axis, so it's going to be like that. Maybe I should make this a bit bigger. Okay, any questions? So this point right here, up in space, that's X, Y, Z. So let's get our X, Y, and Z all down. I got some cleanup work to do, I guess. So this is gonna take a little. This is taking a little longer than I thought. Just give me a sec. I forgot to put my X, Y, and Z in. Oh, I got my Z. Anyway, I'm gonna need some guidance. I'm in so much trouble. Let's I did that. Okay. Okay, so basically the R from polar carries over, I should say in the R in dA carries over into dV in cylindrical coordinates, because cylindrical is just polar coordinates with a z coordinate. So there's not really anything sort of new or surprising here, and I would say that everything is kind of what you'd expect. Okay, and you can identify any point in space using cylindrical coordinates. And you get all the headaches of polar and cylindrical. Let's just go ahead and do the elementary graphs. So maybe the reason why it's called this is called cylindrical coordinates. The first one is r equals k, a constant. And of course, that's just a circle. But in cylindrical coordinates, it's a cylinder. I can decide if that's level or not. So I'm going to tweak it and make sure it snaps. There we go. Any questions? So that's the first of the elementary graphs where r is a constant. Yeah. So it's not really new, but just a little different kind of perspective on that. Secondly, if theta is a constant, I'll say theta equals theta naught. Well, we just have to think about all the points that have the same theta angle. Okay, so maybe I would extend sort of a ray coming out like this. A copy of it. Put it up here. Okay, and then my angle here coming up from the x-axis is my theta naught angle. Like that. So that's a plane, a vertical plane. Okay, so any questions about this? Sorry. Beautiful. Is there any questions? I'm gonna try to fix this, but I'm not gonna take much more time. I'm having trouble. That's all I can say. Okay, any questions out there? I don't see anything. Okay, so that's one of the elementary curves. It's probably worth doing a cone. We haven't done much with cones in this class, but let's just toss another one in there. This is not what I'd consider an elementary cone, but it's a simple surface. Okay. I think I can squeeze this in. Yeah, maybe if I go to the next page. So 3, the cone is z squared equals x squared plus y squared, but that's r squared. So z squared equals r squared, or if you like, z is plus or minus r. Okay, so I usually think of this way. Just kind of 2 lines. Now, if I had an r axis, let's say it was going this way, I don't. And but if I had an r axis, it would look like that. Now I'm going to do a little guideline or two here, so forgive me for a sec. And so if that was an r axis, and then vertically I had a z axis, it would come up. So here's z, and then this side on the right would be z equals r in the zr plane. And of course the other would be z equals negative r. Okay. And but then r spins around with varying theta. So then the next thing I would do would be just sort of try and get an ellipse on here. It's actually a circle. Okay. So this is with varying values of theta. This is unconstrained in theta, so it's almost a cylinder. That is not, so I guess I shouldn't say that. I always say a cylinder is always unconstrained in one variable. This is unconstrained in theta. Okay, but let's go ahead and dump that r axis and just go ahead and call it y. Okay, so I'm going to go ahead and just refer to this as y over here, and then I'll have an x-axis kind of come out like that. Okay, so that's the cone. We normally just say z equals r. Okay, you don't need a negative r. As long as you if you let r go negative, then you get the top of the cone. If you don't allow r to go negative, then z has to be negative r if you want the bottom of the cone. So all I did was I just moved that down below, and that gives me the bottom of the cone. So you can have a top and a bottom cone like that. Okay, any questions about the cone? So these are just, like I said, they're sort of elementary surfaces. Spheres are sort of obvious. So I want to go ahead and I got a couple examples here I'd like to do. So let's move on past this, if you don't mind. So 4. Nope, not a 4. We're ready for examples. Let's leave that up for you. Okay, so the next example will be some integrals. So I want the moment of inertia. Again, it's going to be around a z-axis. So find the moment of inertia about the z-axis. For a sphere of radius A, whose density at xyz is inversely proportional to the distance from the point to the z-axis. So it's similar to the last example I did. Okay, so let's see. Let's just do the distance from the point x, y, z to the z-axis. And that's just r. But we'll just go ahead and say that that's our delta. No, the distance is just the square root of x squared plus y squared. Yeah. And density, remember I use a delta for density. The book uses a rho. So delta of x, y, z is inversely proportional to the distance. So you need a constant of proportionality and you multiply by the inverse of the square root of x squared plus y squared. Okay, so any questions about that? Okay, and of course you may as well put this into cylindrical right now. X squared plus y squared is r squared. And r is positive. These are distances, so you can just say k over r. Reminding yourself, you can't do plus or minus or anything like that. Technically, the square root of r squared is the absolute value of r, but r is positive. I guess r is greater than equal to 0. How about that? Okay. So I have a density function. And it's a sphere, so I better describe the sphere here. So, and it's a sphere of radius A, so let's do that. Sphere of radius A is just x squared plus y squared plus z squared equals a squared. Any questions? Okay. Don't forget x squared plus y squared is r squared, so we're going to have to do this r squared. So the sphere is actually r squared plus z squared equals a squared. So if we solve for z, we'll get z is plus or minus the square root of a squared minus r squared. So that's the bottom and top of the sphere. And so now I'm trying to draw another sphere. Oops. Sometimes I don't understand. There, that's good. All right, and then the sphere. Really? Okay. Any questions? Okay, so then I'm just going to bring up the formula for the moment of inertia. The moment of inertia, again, about the z-axis. So it's a triple integral over r solid, which I'm calling q again, my favorite letter for solids. And then you take the distance squared to the axis of rotation. Distance squared is x squared plus y squared. And then times mass, which is density. And volume. Okay, so that's the same formula as before. Any questions? All right, and then let's see here. So we're going to do triple integral over q. We keep the x squared plus y squared. Delta was just, well, it was k over the square root of x squared plus y squared. So I think I'll keep that k over square root of x squared plus y squared, and then dv. Okay, so that's distance squared, and this is density, so delta of x, y, z, moment of inertia. It's mass times distance squared. Okay, any questions? All right, then we get to evaluate it. So here goes. Okay, so the limits on z always have to be lower surface to upper surface if it's the innermost. The x squared plus y squared gets to be r squared, and density is just k over r. So in the end, you get r squared times k over r. And then don't forget that dv is r dz dr d theta. That's a mouthful. Okay, so I get another R in here. Okay. And then the integral. Okay. So we have to do surfaces on Z. Z is always going to be bottom to top. So you're going to have a bottom surface. To a top surface. Okay. Okay, so the bottom surface is negative. Let me see if I'm going to zoom in on this. So the bottom surface is negative square root. I think it was a squared minus r squared. And the positive square root up here. Okay. And then you're integrating over a region R in the xy plane. So I'm just going to put a big R out there for a sec. And I'll put the R in the diagram as well. And I'll do a little work shading just to say I did it. Okay, so R is shaded in gray in the diagram above. And I'll go ahead and just do a quick job on the rest of the sphere. Okay, so I'm once again trying to indicate, how the geometry works for limits in polar. So we need R to go from 0 to the radius of that circle. Which is A, I guess. And then theta needs to go all the way around so we cover the whole circle, 0 to 2 pi. Okay. Now, lovely. So it's not going to be great. And some of this integral, we'll see, but some of this is going to be ugly. So let's go a step at a time. So we're going to first do with, well, we can clean up. So real quick, integral 0 to 2 pi, integral 0 to A. And I guess we should have put the K out front. So pardon me while I fix that. So K goes there. And then the integral from the bottom to the top of the sphere. Spheres are a bummer in cylindrical, or they can be. As you can see, this is not great with these limits. Don't like it. Spherical coordinates would be so much easier. We'll do that next. Or we'll do it soon, I should say. Okay, so there, and then, so what do we get all together? Just a kr squared, right? Because the two of the r's cancel, so we just get an r squared, and then dz dr d theta. I don't really like the looks of that because integrating r squared times the square root of a squared minus r squared sounds pretty bad. So we'll probably get a little help from our friends on that. So you decide you're going to have an r, oops, that r squared still, but times z. We're integrating dz right now. So you're going to have r squared z, and z is going to go from the bottom to the top. Like that, and then we'll have a dr d theta. And then you just get two of those, I think. Okay. Let's see if I can take advantage of some of this space here. Oh, there. Okay, like that. So you're gonna have the same thing. You're gonna have two of these. So it's gonna be a 2k integral from 0 to 2 pi, integral from 0 to a, and then you just get an r squared times the square root of r squared, square root of a squared minus r squared, like that. That'll be dr and d theta, as so. Okay, so I haven't done anything tricky yet. But the tricky part now is to recognize that that inner integral does not involve theta. So given that there is no theta anywhere, including the limits, that can factor out. So you could do it this way. 2k, you could do theta first, 0 to 2 pi d theta. And then the next integral from 0 to a of r squared times, square root of a squared minus r squared dr. Okay. Okay, any questions? Can the differentials be in any order? Yes, but you won't encounter it. Cylindrical coordinates, let's just say this is the normal order. It's the natural order for cylindrical. So I don't think you'll see anything that's not in this order. It would be really a real drag to have R be a surface as a function of theta. I just hate the thought of that. So don't get worried about that. Okay. Okay. Just we'll keep it with this order. Now we can go ahead and just call that first integral a 2 pi. So here you're going to have 2 times the integral from 0 to 2 pi of d theta, that would be 2 pi. And there's a k. And then now the last part, the integral from 0 to a of r square, square root of a square minus r square, dr. Now the normal approach to this is to do a trig substitution. So this is going to be a little tricky because we've already gotten rid of our theta. Let's use a t instead of a theta just to keep it simple. So you could say that r squared, sorry, that r could be a, we could do a cos t. So a square minus r square would be a square minus a square cos square t, which is when you factor it, you're going to get an a square sine square t, like that. Okay. And so let's see how this plays out. I think we've got a 4k pi and an integral. I'll worry about the limits in a second. R squared is going to be a squared cos squared t. Like that. And then I'm using a t to stand for theta, sort of. And then the square root of a squared minus r squared is the square root of a squared sine squared t. So this will be square root of a squared sine squared t, like that. Now dr would be negative a sine t dt. So I'll have to have a minus sign out in front of all this. Like that. And let's put in an a sine t dt, like that. Not a big fan of these even powers on an integral. I'll put limits on in just a second, real quick here. So I think I've got an a squared times another a squared. It looks like a to the fourth. So what about negative 4? A to the fourth k pi. We'll be integrating, I think, cosine squared times sine squared t. Right? dt. And I'm going to assume that t, I need, is the sign, so I need t to be between 0 and pi. Okay. And let's make sure that works out with these limits, because if it's not, then I'll have to worry about that. All right, so when r is 0, I need a cos t to be 0. So let's say if r is 0, then the cosine would, I guess we would need t to be pi over 2. Cosine of pi over 2 is 0. And if r is a, then I need cosine t to be 1. So t will be 0. And as a rule of thumb, whenever your differential comes out negative, the limits will end up backwards. I've said that before. This integral is going from pi over 2 to 0, like that, which is great because those are backward and the integral came out negative, so this is just exactly what we want to see. So let's write 4 a to the fourth k pi integral 0 to pi over 2 of cosine squared t sine squared t. Okay, and here goes. So the cosine square is going to be 1 plus cos 2t over 2 times sine square, which is 1 minus cos 2t over 2 dt. And that's the difference of squares. The 2's will cancel the 4, so we're just going to get a to the 4th k pi integral from 0 to pi over 2. And it looks like 1 minus cos square dt. Okay, that's not too bad. Still got an even power. So here goes again, another power reduction. So we got a to the 4th k pi integral from 0 to pi over 2. So it's 1 minus, here goes, 1 plus cos 4t over 2. Okay. dt. So a to the 4th k pi integral 0 to pi over 2. Like that. It looks like we've got 1 minus a half, so I think that's just going to be a half minus 1/2 cos 4t. Okay, any questions? That looks pretty easy now. Antiderivative of cosine is sine, so we're just going to have a to the 4th k pi, and then we'll just have a t, one, I should say a half t, where t goes from 0 to pi over 2. Okay. And 1 minus an 1/8 sine 4t, where t goes from 0 to pi over 2, and that's going to come out 0. Sine of 0 and sine of 4 pi over 2, that's sine of 2 pi. So that whole thing is just going to be 0. Okay, so I think it's a pi over 4 in there. So it looks to me like we're getting an a to the 4th k. There's pi times another pi, so it looks like pi square over 4. Okay, there's your moment of inertia. Those have to come out positive. Okay, so when you say what I did there, I'm going to need a little more help about what you're referring to. So do you mean the antiderivative of cosine? Third to the last. Do you mean this one? And then how did I get to there? Yay or nay? No, to the line before it? Okay, well, let me make sure I didn't make a mistake. So I think what you've got there is 1 minus a half minus a half cos 4t, yeah? Oh, the line before that? Oh no, is that what you mean? So I'm just referring to this part here. So you get a half minus. So you're talking about Is that what we're talking about? Never mind. All right. Well, as usual, hopefully this is without any errors, and looks pretty good. So let's just assume it's good, and let's see what time is it. 7:30. Let's take our break.